Okay, so now we've looked at a whole lot of different methods, algorithms, tricks to actually finding derivatives, and we've looked at a lot of different types of functions, polynomial in nature, rational functions, trigonometric functions, inverse trigonometric functions, and we've even looked at implicit differentiation as a way to maybe find derivatives of things that are even more complex, like we actually use them for the inverse trig functions. Both of my cats are hanging out, so we'll see it. Hopefully they won't bother us. Now we actually want to look at something, maybe the last type of function that we're really going to look at in this class and try to find its derivative. And we're going to start with exponential functions, and in particular, the exponential function y equals e to the x. And our goal is going to be to find dy dx, y prime, whatever you want to call it. Find the derivative. And as far as it goes, well, we can just take the limit definition. So let's see, y prime dy dx is equal to the limit as h approaches 0 of e to the x plus h minus e to the x all over h. And now as far as this limit goes, I can factor an e to the x out of both of the terms on top, and I'll get the limit as h approaches 0 of e to the x times, if I factor in e to the x out here, I'm left with e to the h, minus if I factor in e to the x out here, I'm left with a 1 all over h. And now, here, this limit is a limit with respect to h. This e to the x has no h in it, which means from the perspective of the limit, it's just a constant, so I can pull that out. So I'm left with e to the x times the limit as h approaches 0 of e to the h minus 1 over h. And now the question is, what in the world is that limit actually equal to? And as far as it goes, with the tricks we know right now, easiest way to actually solve that is to just throw it into a calculator, and I'm not going to stand here in the video and use a calculator. If this was a class, I would just randomly pick on you people and make you throw random h values in there as h gets really small to see what actually happens. But if we do that, this whole limit right here, if you just plug in values into a calculator as h gets really small, you'll see that that actually approaches 1, which means this is equal to e to the x times 1, which is just e to the x. And now we're left with kind of this slightly bizarre thing where y is equal to e to the x and y prime, its derivative, is equal to e to the x, which means the exponential function e to the x is the function that has itself as its own derivative. Which is, again, a little bit bizarre. It's the only function like that, which means if nothing else, it'll be easy to remember. But there are actually other ways to show this, but they require more complex math. You actually see it in Calc 2, and we derive this in Calc 2. For right now, like I said, the best we can do with this is to just plug it into a calculator and see what you get and go from there. But now, well, that derivative is really easy, but from that one derivative right here, we can actually get tricks to finding a whole lot more derivatives. And that's what we're going to spend the rest of this video doing. But first, just so we're clear, suppose we have y equals e to the x squared plus 3. That's just an exponential function, but now the power is changed, but I understand that's just a composition of functions. This is the inside function right here. So if I want to get the derivative of the outside, that's the exponential function. This is inside the exponential. The derivative of e is just e, or the derivative of e to the x is e to the x. The power stays the same. That's the inside, so it's staying the same, times the derivative of the inside function, which is this. And that's just 2x. And there is kind of an idea here, and again, I actually say this as clearly as possible. If you have an exponential function, if you're taking its derivative, if your derivative does not include the exponential function, then you're wrong. Because of the way this works, you have to get the exponential function as the derivative. Admittedly, there may be times if this gets more and more complex where you might factor it and make it look slightly different. But when taking your derivative, if you have an exponential function, your derivative has to include the exponential function because that's how it works. This is, if you will, e to the y, where y is that function. The derivative has to include e to the y, e to that function, times the derivative of the power right there. So just keep that in mind. Suppose we have y equals e to the x, e to the x plus 2. Now again, how you choose to find the derivative, we've said this before, is kind of up to you. One thing you could do is say, oh, okay, that's the product of two exponentials, product rule. It's the first e to the x times the derivative of the second. The derivative of e to the x plus 2, rewrite the exponential, then take the derivative of the power, chain rule. The derivative of that's just 1, so it doesn't matter. Plus the second, e to the x plus 2, times the derivative of the first. The derivative of e to the x is e to the x. And then you can actually clearly simplify that. Let's see, there's clearly just two of the exact same thing. So it's 2 e to the x plus 2. But then, you know, rules of exponentials, if you multiply two exponentials together, you add the powers. So that becomes 2e, x plus 2 is 2x plus 2. And there's my derivative. But if I use these rules of exponentials at the ending, why don't I just use them at the beginning? So I could have just said y equals, multiply two exponentials together, add the powers. That's e to the 2x plus 2. Now take the derivative. Derivative of the exponential, rewrite it, times the derivative of the power. The derivative of 2x plus 2 is just going to be 2. And then I get 2 e to the 2x plus 2, which is the same thing I got here. So it doesn't actually matter which way you do it. You can use any algebraic trick you know, any differentiation trick you know. As long as what you do is mathematically, algebraically sound, you'll end up getting the right answer. But, like I said, if we can get the derivative of the exponential function y equals e to the x, there's actually a lot more exponential functions, and we want to take the derivatives of those too. So for the sake of argument, suppose we have y equals a to the x, where a is any base, not just e. How do I do that now? Like over here on the side, we won't solve this out yet, but suppose I actually had, if it helps, y equals 2 to the x. What's the derivative of that? If the derivative of y equals e to the x is e to the x, then is the derivative of 2 to the x 2 to the x? It's an exponential, maybe. Although I did kind of already say that the exponential function e to the x is the only one that has itself as a derivative. So it's a little bit unlikely, maybe. But how do we show it? And now, to do it, we can actually use a trick. And let's see, which trick do I want to go with? Your book uses one trick, but frankly, I don't actually like their trick, so I'm not going to use it. So your book actually derives this out one way you can look at it. I have another way that I prefer. I want to take the derivative of this. Well, the problem is that x is a power, and I have no idea how you take the derivative of x as a power like that. So I want to get rid of it. As I've said before, algebraic tricks are good. Go back to your 171 class. How do I bring down powers of exponentials? They have to be logs. So I'm going to take the natural log of both sides. ln of y equals ln of a to the x. Trick you use in 171 to solve exponential growth problems, applications. Now, the log of something raised to a power, the power can be brought down in front. And you have ln y equals x ln a. Now take the derivative. Well, let's see. Over here, x ln a. Keep in mind, ln of a is just a constant. So this is just a constant times x. The derivative here is just a constant. What's the derivative of ln of y? Well, that's a little bit more bizarre, but maybe we can do that separately. Let's see, if I want to find the derivative of ln of y, well, suppose I just said y equals log base e of, we'll go with x. Interchanging the letters here, so don't confuse these. But if I wanted to find the derivative of the natural log function, we know the natural log is log base e. Take the derivative here. Well, again, I'm kind of stuck where I can't take the derivative of a log because I don't know how to. That's actually why we're doing this. But apply the definition of the log. Log base e of x equals y means e to the y equals x. Now that I can take the derivative of. On the right, the derivative of x is just 1. On the left, the derivative of e to the y, that's implicit. I rewrite the exponential. Then I take the derivative of the power. The derivative of y is y prime. Now, to get y prime, divide e to the y. I get y prime equals 1 over e to the y. Y is log base e of x, so I end up getting y prime equals 1 over e to the log base e of x. And if you remember your rules for logs from 171, e raised to log base e of x, these cancel, and you're just left with x. So y prime equals 1 over x. Now I get, don't jump up here, cat. Now I get the derivative of the natural log function is 1 over x. So over here, ln of y, the derivative would be the same. We do it implicitly. It's 1 over y, 1 over the inside, times the derivative of the inside, which is y prime. Now, multiply by y, and I get y prime equals y ln a. I know what y is. It's right here. Y is a to the x. So y prime equals a to the x ln a. And now we've kind of killed two birds with one stone here, whereby we can say, if I have the function y equals ln of x, the natural log function, the derivative is 1 over x. If I have another exponential function y equals a to the x, the derivative is a to the x ln a. And I'll point out it actually follows that rule we said with e to the x. If you have an exponential, when you're doing the derivative, you have to write the exponential. A to the x, a to the x. It has to be in your derivative. Then you do ln of the base. So over here, if y equals 2 to the x, y prime, it's rewrite the exponential always, ln of the base, 2. The last thing I'll actually point out, this rule actually applies to the exponential function e to the x. We just couldn't do it because we didn't know the rule when we were deriving this. But y prime, according to this rule, I rewrite the exponential, then I do ln of the base. The problem is ln of e, well, those cancel out, and it's just 1. Which means y prime is e to the x. So there's actually different ways you can kind of manipulate, as long as we understand if y is a to the x, y prime is a to the x ln a, e to the x, the derivative is e to the x, and if y is ln of x, y prime is 1 over x. I'm going to make another video doing some examples of these.